Okay, make sure that you have your notes out so that you're ready to fill in your slotted notes as we go through the information on covalent molecules. So a lot of this is going to be review. This is naming covalent compounds. There's nothing for you to fill out here, just a nice review because your practice will ask you to name the covalent compounds as you draw their Lewis structures. Diatomic elements are simply covalent molecules that are made of the same element. There are 7 diatomic molecules for you to memorize: hydrogen, nitrogen, oxygen, and the first 4 halogens. So if you remember H and OH, that's a good acronym to help you. There is also a mnemonic device. Have no fear of ice-cold beverages, because you should have a fear of beer because your brain isn't finished growing yet. So if you kill brain cells, that doesn't only kill your current brain cells, but it also kills the potential of future brain cells. So you should have a fear, but it's a good mnemonic to help you to remember the diatomic elements. One of the main things you're going to be doing is creating Lewis diagrams of different molecules. You already did an ed puzzle practicing this a little bit. We're going to practice a little bit more together. So when you have a diatomic molecule, you don't have to have rule number 2 because there is no central atom. So you do start with counting your valence electrons. So here hydrogen just has 2. Then you draw your single bond between your 2 atoms, and remember that that line represents a bond of 2 electrons there. So I've got 1 here, 1 here. Each of the 2 has completed their duet, so I'm good with hydrogen. Oxygen, a little more complicated. Each oxygen has 6 valence electrons, so here I've got a bond of 2. So that leaves me with 10. So I'm going to distribute 5 to each oxygen. That means this oxygen has 5, 6, 7. It's still lacking 1 electron to fill its octet, so it's going to share 1 so it can gain 1. And so the other oxygen is going to do the same, so they each have 2, 4, 6, 8, 2, 4, 6, 8. We've completed our octets. Still with 12 valence electrons. 1, 2, 4, 6, 8, 10, 12. And then here with nitrogen, we're doing the same thing. Each nitrogen has 5 valence electrons. I'm going to go ahead and bond those together and distribute the remaining 8 evenly to each nitrogen. So I've got 2, 4, 6 for each nitrogen. Each nitrogen still needs 2 more to complete its valence, which means there needs to be 2 additional bonds. So we're just going to turn some of these lone pairs up here into shared bonds. So 2, 4, 6, 8, 2, 4, 6, 8. More commonly, though, what you're going to be practicing with is bonds that do have central atoms. So you're going to need to use that number 2. So this example here with water, oxygen has 6 valence electrons. Each hydrogen has a single valence electron for a total of 8. By creating these initial bonds here, we've completed our duet, and we've used up 4 of our electrons, so 2, 4. My hydrogens are happy, so my additional 4 are going to go to my oxygen, and my oxygen is now happy. 2, 4, 6, 8. This one has 2. This one has 2. We're good. Carbon dioxide. My carbon has 4. Each of my oxygens have 6 valence electrons, so that's a total of 16 valence electrons. 2, 4 to get those carbons and oxygens together, which means I have 12 more to distribute. I'm going to give 5 to each oxygen and the remaining 2 to my carbon, which means that my oxygens each have 2, 4, 5, 6, 7. They need 1 more. 1, 2, 3, 4, 5, 6, 7. Carbon has 2, 4, 5, 6. It needs 2 more. So again, we're going to share 1 here, share 1 here. We give a double bond, 2, 4, 6, 8 for carbon. 2, 4, 6, 8 for this oxygen, 2, 4, 6, 8 for that oxygen. All right, every once in a while, you may have a situation where you only need one additional bond to complete the octet for all, or one double bond. And it doesn't matter if the central atom is the same as your terminal atoms, but your two terminal atoms should be the same because they're going to bond in the same way with your central atom. As long as your terminal atoms are the same, it doesn't matter if you put your double bond on the right-hand side or the left-hand side. Either one is correct. In fact, in reality, what's happening is the electron is, one of those electrons is kind of being shared kind of back and forth, and that's why it's called resonance. So sometimes it does look like this, sometimes it looks like that. But what you need to know for right now is that either one is correct. It doesn't matter which way you draw it. Here is what we're doing, the new thing that we're doing here is determining if a covalent bond is a polar covalent bond. So we've already had experience with talking about that ionic bonds are very polar, right? We have an extreme positive ion and extreme negative ion. So we've completely transferred electrons and created ions there because there's such a big difference in polarity. Some covalent bonds also can have a polar component to them. They're not as polar. This little slide here is not on your notes, but this kind of shows you the math behind it. So the electronegativity of each element on the periodic table has a specific value. And when you take the difference between the electronegativity of the different atoms that are bonded together, if they're a high enough number, they're an ionic bond, so the electrons are totally transferred. If they're not, really, really close, they're not going to be, the electrons aren't going to be evenly shared. They're going to be unevenly shared. So the electrons are going to go and kind of hang out more with the more electronegative atom. So it becomes a polar covalent bond. So fluorine tends to hold on to more of the electrons, and hydrogen tends to be more positive and not hold on to those electrons. So that's what we call a dipole. So if we have a dipole, that's a polar covalent bond. And so we'll kind of look at how to identify that. A dipole is just simply a place where there is a positive charge and a negative charge on an atom. And if the direction of the pull of the negative electrons cancels each other out, we have a non-polar molecule. Or if there's not a difference in charge at all, we have a non-polar molecule. But we can't have a dipole that has a nonpolar molecule if they cancel each other out. So you can see that this one is pulling some electrons in this direction, this one is pulling some electrons in this direction. So we have kind of even pull, it's nonpolar. But here, the electrons are being pulled both kind of up toward the oxygen. There's not anything canceling out that pull in the opposite direction. So this one over here is going to be a polar molecule. All right, so these are the rules for identifying if a molecule is polar really quickly. So we don't have to add the electronegativity values or anything like that. Really, you're just looking at these basic rules on what is the central atom and what's attached to it. So here I've got my central atoms, and the first rule to determine if it's nonpolar is that there's no lone pairs attached to the central atom. We don't care about the terminal atoms at all, but here you can see that nitrogen has a lone pair. So that has a lone pair, then that means it can't be nonpolar, it's got to be polar, right? The second portion of the rule is that the terminal atoms are the same. So here I have a central atom, chlorine, chlorine, chlorine. That meets both rules. That means it's probably nonpolar. Here I've got my central atom carbon, hydrogen, hydrogen, oxygen. They're not the same. So this is probably polar. So pause it for a second and see if you can identify the last two. Hopefully this is what you identified. and make sure that you go back and answer your essential questions, and then you'll be finished with your notes. I hope this was helpful.